And same time as well. So if you have any conflicts with the exam, make sure to email both your recitation TA or me, and make sure to copy Dr. Baker on that. He's going to be the one managing all those things. So then the due date for homework 9 got pushed back to after the exam, and then homework 10 is due the same day that it was before. And doesn't seem like that far away, but November 22 is our last day of class. So coming down the home stretch here already. It's hard to believe. I hear you guys crying out there. I know, it's terrible. Any questions about homework or the exam or anything before we jump back into our lecture today? So it's so dark out right now, isn't it? I'm ready for that time change to happen. I think it's this weekend, yeah. All right, well, again, I think you guys all should have seen that email from Dr. Baker this morning. Make sure to check the attached. There was a document attached to that had a lot of the same stuff on it. So I would refer you to that if you're having any questions. All right, so we're going to resume our discussion and hopefully finish up chapter 18 today. Remember, here we're talking about inference for one population mean, which is kind of coming back and hitting again what we saw in chapters 14 and 15. Chapter 14 and 15 we talked about confidence intervals, but we had that sort of unrealistic assumption where the population standard deviation was known. We knew what sigma was, and we had some formulas there. But now we're kind of addressing that assumption, which is pretty unrealistic. So what we got through in class on Friday was this new formula for a confidence interval, which kind of same setup. We have a simple random sample from a large population. Our confidence interval is going to be x bar plus or minus t star times s over the square root of n, where t star is that new critical value we looked at. And just a reminder, this is kind of what we're going to use in practice. So in chapter 14, we introduced the confidence interval that had a z star and a sigma in that. But because we'll essentially never know what sigma is, we need to do something about that. So we have this new formula, which is x bar plus or minus t star times s over the square root of n, where this is, of course, the sample standard deviation. So the idea is exactly the same. The formula changes, and really the only sort of the main difficulty here is that we're now using a t star instead of a z star. We talked a little bit about the table, table C, I believe it is, which has a slightly different way of finding what that critical value is, but actually I think it's a little easier than the z star was. You just have to take care of a few details there. So we're fixing our issue with chapter 14, where we had this formula, which is something we can't actually use in practice. We fixed that there, and now we're going to move on to kind of addressing the same issue that we had with our hypothesis tests in chapter 15. So kind of the same idea here. Just a reminder that if we have this thing here, x bar minus mu divided by s over the square root of n, this thing has what we looked at this last time, a t distribution with n minus 1 degrees of freedom. And we talked a lot about what that t distribution was. We saw that it was similar to the normal distribution. It was symmetric. It was sort of bell-shaped, unimodal, but it had sort of heavier tails is what we came to conclude. So we're going to use the same idea for our hypothesis tests. And really, it's going to be sort of like the confidence interval thing that we just looked at. The ideas are all exactly the same. The formula is changing slightly, so that'll change our test statistic, and that will change how we find our p-value. But otherwise, it's going to be exactly the same as it was before. So let's take a look at this. So if we want to test our hypotheses, again, the hypothesis setup is going to be exactly the same. We'll do an example later, and we'll look at that. So if you want to test a hypothesis that mu is equal to some hypothesized value, so remember that mu 0 is the hypothesized value. And by the way, we are now on page 5 of the chapter 18 notes, picking back up there. So if we want to test this hypothesis, sort of the more realistic situation we'll be in now is we can calculate this thing. So we're going to take x bar minus mu 0, the hypothesized value, and divide it by our sample standard deviation over the square root of n. So this is the new test statistic. So you remember before it was a z, we called it was x bar minus mu 0 divided by sigma over the square root of n. So again, looks very similar here, right? So we're just swapping out the sigma for the s, and that's no problem. We can do that here, and it just changes the distribution of that test statistic. It's a t instead of a z. So if we want to test the same hypotheses, have the same setup, we want to do this test. That's our new test statistic. And now the p-value, again, the idea is exactly the same, but how we actually calculate it is going to change slightly because we have a t distribution instead of a z. So this picture over here is the pictures are going to look kind of the same, but just remember we're dealing with a t instead of a z. So if our alternative hypothesis is that the mean is not equal to our hypothesized value, then we're going to take our p-value is going to be both of those tail probabilities. We're going to find the area of one of those and multiply it by 2. That's what our p-value is going to look like. If our alternative is less than, the mean is less than some hypothesized value, kind of similarly our p-value is going to look at the area less than that test statistic we got. So again, kind of the thing that you can match up here is that the inequality sign in your alternative hypothesis should line up with your p-value, the formula for a p-value there. And similarly, if we want greater than, we're going to look at the area to the left, to the right rather, of our test statistic. So exactly the same idea. Again, these pictures should look very similar to what we saw in chapter 15. Just how we actually calculate the p-value is going to change ever so slightly. Is that okay so far, what we're doing here? Any questions you guys can think of? Okay, so this again very similar idea as what we were doing before. So let's take a look at doing an example of one of these. Let's flipping over a page here, kind of show you how we're going to go about doing this. So here in our example, we're going to go back to the screen time example that we saw back in chapter 15. So back in 15, we saw that we knew that a recent study found that the average screen time for children under 12 was 6.1 hours. And so we believe that Lucy's average amount of screen time would be lower than that since we know that her parents are trying to monitor the amount of television she watches. And so here we have data on Lucy's television watching, for a random sample of 36 days. And we want to test our claim at the 0.05 level of significance. Okay, so that's the setup, and the first thing that I think is in your notes there is to actually take a look at what this data is. So we're going to take these 36 numbers here. We can throw them into jump, and we can do some things same kind of things we did back in chapter 1, chapter 2. We can look at a histogram of those values, and there we have some summary statistics. We have the mean, the standard deviation, and then some other information there. So we'll come back to this information, but just keep your eye on that as we move forward. So again, kind of going through this process of the state plan solve conclude. We're going to kind of step through this very, very formally and very slowly to kind of make sure that we know what's going on here. So again, the state step, we kind of want to rephrase the question that we're interested in, taking what can sometimes be confusing wording in the problem and turning it into something that we're familiar with seeing. So what the example actually says is that you believe that Lucy's average amount of screen time would be lower than that, again, kind of overthinking about it, of other children under 12, since her parents' efforts to monitor the amount of television she watches, since they try to lower that amount. So kind of thinking about this in terms of the formal language that we use in these hypothesis tests, what we can say is that In other words here, this is saying we want to know, is there evidence to conclude that Lucy's average daily screen time and then what do we want to test about what this average daily screen time is of Lucy's? What do we want to compare that to? Yes, right. So we want to compare this to other children, and specifically, how do we want to compare it, or what do we want to see? If it's lower than, right? So the question says we believe that this might be less than that of other children. So we want to see if Lucy's average daily screen time again is lower than or is less than that of other children under 12. So again, the question that we sort of, maybe the language you'll recognize here is a question like, is there evidence to conclude that Lucy's average daily screen time is less than that of other children under 12? So again, the language in the example or in the question, in your homework question or something, might not always be as clear as this, so just kind of practicing going from what the example says to what our sort of the question that we recognize there is. So is there evidence is kind of our tip-off that we're doing a test of significance here. All right. So that's kind of restating the question in everyday language. So let's think now about what our hypotheses will be here. So again, let's just write down what mu is. So again, from our question of interest here, what we're checking about is Lucy's average daily screen time. That's what we want to try to say something about that. Is it less than that of other children, or is it not? So that's going to be our parameter of interest here. So mu is going to be equal to Lucy's average daily screen time. And so we want to set up our hypotheses. We have our null hypothesis. We have our alternative hypothesis. Both of them involve mu. And remember, the null hypothesis is going to always have an equal sign in it. So we're always checking mu equals something. So what's my hypothesized value here? What am I interested in comparing Lucy's average daily screen time to? 6.1, right. I want to compare it to that of other children under 12, which from our example, we see that the average amount for children under 12 was 6.1 hours. So exactly right. Just like before, we're going to fill in a 6.1 here. So once you have your null hypothesis set up, the same number goes over here in the alternative hypothesis, and we just have yet to fill in what the inequality there is. So do we want to know if Lucy's average daily screen time is less than, greater than, or simply not equal to 6.1? Less than, right, exactly. So that's just kind of taking what our question is. So we want to see if her screen time is lower than or less than that of other children. So we want to see if mu is less than 6.1. So again, this is kind of maybe this seems simple here, I don't know, but this is kind of, I think, one of the hardest parts of these problems is figuring out what the heck are they asking me to do, and then can I translate that into what my hypotheses are. So is this okay with everybody? Can you guys think of any questions on how we just set this up? So in your homework problems, I would highly encourage you to kind of, before you just launch into writing out formulas and whatnot, is really kind of make sure you have this part nailed down, and then the rest of the stuff sort of follows more steps there than we have for this part of the example. Okay, so there's what our hypotheses are. The other part of our plan step is that we want to check our conditions. We want to make sure that we can actually use this procedure. And At the end of lecture, I think we're going to have a little time. There was a document posted on Carmen that really kind of laid out these conditions that we've been looking at for the last couple weeks here in a very formal way. So we'll come back to that. But again, the three conditions that we always have. What are those three conditions that we always have? The names of the conditions, or what's one of them? Yes. So we want to see if it's a random sample. What's another one? Small enough, exactly. Is our sample small enough? And then thirdly, what do we have? Yes, right. So we want to make sure it's small enough, but we also want to make sure it's large enough. All right, so first question is, do we have a random sample? What do you guys think? Yep, the usual thing, right? So it's stated in the problem. We have a duh there. But again, just kind of formalizing, we do for sure have a random sample. All right, so the next question is it small enough? And this we just want to make sure that our sample, our population rather, is at least 20 times larger than our sample. So we take 20 times n, which is equal to, here my sample size is 36, so 20 times 36, 720. And then kind of like we saw back when we were looking at this before, this is less than all of Lucy's days. So again, we're not looking at too many of her days here. So we're good to go there. And our large enough sample here, again, we have that n is equal to 36. So what can we say about n being equal to 36? It's less than 40, right? So that's kind of what you hope for, is that your sample size is bigger than 40, because then you don't really need to even look at the data. You're always good to go. But since it's less than 46, remember in this chapter that just means we need to look at the data. And actually, I think I have this. Yeah. So again, if our sample size is less than 40, we need to think about what the data is, or take a look at it. So I put this slide up again here. This is from earlier in chapter 18. This is on page 2 of your chapter 18 notes. So again, our large enough sample condition is that if the distribution is not normal, which we're not told anything about that, and our sample size is less than 40, we still have a chance of using these procedures. So again, our sample size is 36, so n equals 36. So we're in this sort of this middle situation here. So we can use, it says that the condition says we can use the procedure except in the presence of strong outliers, or strong skewness. So what I mean by that is, looking at the actual data that we have, do you guys see any outliers or strong skewness in this data set? So again, looking at the histogram, looks okay, right? Pretty symmetric. Actually, looks really nice. So definitely no outliers, and not really any skewness either. So even though our sample is less than 40, even though our sample size is less than 40, again, because there are no outliers and no real skewness, we're okay here. So even though our sample size is less than 40, because the data is looking pretty standard, we're in good shape here. So therefore, we can put little check marks by each one of these conditions. So again, I'll come back again. When you're checking conditions, the first two are always the same. Always want to see, do I have a random sample? Is my population at least 20 times bigger than my sample? The third one's going to change a little bit, so I'll come back and we'll talk more about that at the end of class, just kind of review exactly what all these conditions are. Okay, so we've kind of stated what our problem is. We've planned, we've written out our hypotheses, and we have made sure we can use these procedures. Since we can move on to the solve step here. And our first our thing here is going to be the test statistic. So remember, our t is going to be equal to x bar minus mu 0 divided by s over the square root of n. So let's quickly jot down what all of these things are, and we can then just plug them into our equation and go. So again, in the example, most of the examples that we look at on this page here, they'll often tell you what the sample mean is, right? They'll say they took a random sample of 36 days and found a mean of whatever and a standard deviation of whatever. If you see a homework problem like this where they don't straight up tell you that, then again we have to actually calculate the mean and calculate the standard deviation. And so that's what we've done here. So our mean is going to be 5.02 and our standard deviation is going to be 2.02. So 5.022, and our standard deviation is 2.02. We know our sample size is 36, and then what's mu 0 going to be? Exactly right, 6.1. So again, mu 0, remember, always comes from the null hypothesis. So looking at your null hypothesis here, whatever number is in there is what mu 0 is. So remember, we're assuming that the null hypothesis is true and kind of seeing how unusual our results are. And so we're assuming that the mean is 6.1. We're going to see what our results look like. So mu 0 is 6.1 there. So we can plug all these in. We have 5.022 minus 6.1 over and if you plug those into your calculator, you'll get that this is a negative 3.20. So again, test statistics almost exactly the same as it was before. We just have thrown an S in there instead of a sigma. So our test statistic is negative 3.20, and now we want to go about finding the p-value. So this can be a little tricky with the t-distribution, at least using the table. So I'm going to show you how to do this by hand, and then I'll show you maybe a little shortcut for how we do this as well. So first, let's sketch out a picture of where our p-value is going to fall. So here's our t, centered at 0, and we're interested in down here something about negative 3.20. Remember, the alternative hypothesis said that mu is equal to mu is less than 6.1. So our p-value is going to be equal to the probability that a t random variable, again, is less than negative 3.20. So because the alternative hypothesis had a less than, our p-value is also going to have a less than. And so to shade in kind of what the area that we're looking for on here is, what area do I want to look at here? I think I heard it right. To the left, yes, exactly. I want to look at that probably being less than that 3.2. So this is going to be equal to this, whatever the area of that little the shaded in blue box is. So then how do I find what that area is? So sort of the way that we can do this by hand is we're going to go back to table C. So table C, as I told you before, I think is a little bit easier to find what the critical values are. I think it's a little bit more difficult actually to find p-values, but we're going to show you how to do this anyway, and hopefully it'll start to make sense. So remember that our t is a negative 3.20, and n is equal to 36. So our degrees of freedom, what are the degrees of freedom going to be here for this example? Right, so 36 minus 1, right? 36 minus 1 equals 35. So I need to go onto the table and find the row that corresponds to 35. But 35 is not on there. So do you guys remember what we do in the case that the number we're looking for is not on the table, is not on the degrees of freedom column? Round down, exactly right. So I'm going to round down and use degrees of freedom equal to 30. So even though sort of classic rounding rules tell you 35 gets rounded up to 40, we're always going to round down. So even if that had been a 39, we would round down. So we want to pick out the 30 row there. And then we need to find kind of where our test statistic would fall in this row of numbers right here. So focus in on this row of numbers here, and we're going to take the positive of our test statistic. It's the same either way. So we can see that 3.2 would fall right there between, I don't know if you can see that, 3.030 and 3.385. So let's go back and fill these in on our, so this is going to be not really to scale. This is negative 3.030, and out here is negative 3.385. So I'm just finding the place on the table where my test statistic falls in between. And again, looking at just the positive side of things. So then I'll go down to the bottom of the table, and the last two rows here says one-sided P, and the other one says two-sided P. So do I have a one-sided test or a two-sided test here? Just one-sided, right? My alternative is a less than. So I just have a one-sided, and so I can trace down and pick out these one-sided values. So I have a 0.025. And I have a 0.0025 and 0.001. So what those numbers tell me, those are giving me the area in the tail that's outside of that value. So again, that tells me that probably being less than 3.030 is 0.0025, and being less than 3.385 is 0.001. So let me draw that in here. Maybe this will help. So I'm told something about this red area, and I'm told something about this, let's call this green area out here. So what the table tells me is that this green area is 0.01, and it also tells me that this red area here is 0.025. Sorry.
Does that
0.001.
red area include the green area?
So yes, does the red area include the green area? Yes, it does. So I'm looking at sort of cumulative area out to the left there. Great question. Maybe make that a little more clear. So the red does include, and now I've covered up the green. But so yes, so I'm talking about cumulative area there. So again, the red area is 0.0025, the green area is 0.001. So what does that tell me about the blue area? See if you guys can jump to that. Exactly right. So if you look at the picture there, again, if we're looking at cumulative areas, the red includes all of the blue area, and the blue includes all of the green. So that means that this that means that the p-value is between 0.001 and 0.0025. So again, a little strange, but is everyone with me? Does everyone see what I'm doing here? Okay. So what you need to do is find the correct row of the table, find the two numbers that your test statistic falls in between, and then we can kind of sandwich our p-value between two values there. So we don't know what it is, but we do know that it's less than, we do know that it's between 0.001 and 0.0025. Okay, so now we're ready to make our decision. So our p-value, again, is less than 0.0025. And if we look back up at the example, we know that we want to test our claim at the 0.05 level of significance. So what that tells us is that our alpha here equals 0.05. We're going to go with our kind of classic alpha level there. And sure enough, our p-value is less than that alpha value. So therefore, what are we going to do? Reject or fail to reject the null hypothesis? I think I heard it. Someone in the back? What are we going to do here? Do we want to reject or do we want to fail to reject? Anybody in the back? So our p-value again is less than that alpha value. So do I want to reject or do I want to fail to reject? Reject. I think I heard it. Thank you. So this means that I want to reject the null hypothesis, reject H0, and then I can give my usual conclusion. So again, because the p-value is less than alpha, which is 0.05, I want to reject the null hypothesis, which means that, so my usual interpretation here is that there is enough evidence to conclude, and then I want to kind of say what since I've rejected the null hypothesis, I want to say what the alternative hypothesis says. So we've concluded that Lucy's average daily screen time is less than that of other children under 12. So again, that's what we said is there's enough evidence to conclude that Lucy's average daily screen time is less than that of other children under 12. So we've rejected the null hypothesis. So what the alternative hypothesis says then is that it is less than 6.1. So that's, again, the interpretation has not changed at all. How we make our decision to reject or fail to reject is the same. It's just calculating the test statistic and finding the p-value are the differences here. So what question just came in, why didn't we use 0.001? So thank you, I should have put that in here. So what we found on the previous page is that our p-value is between 0.001 and 0.0025. So again, we don't know what it is, but regardless of what number it is in between those two, it's definitely less than 0.05. So that's again why we said that. And so then again, real quick, why did I choose those numbers? So again, we just need to pick out the two numbers in the row of this table, in the correct row. So we want to be in the degrees of freedom 30 row, again, because that's the closest degrees of freedom that are listed there. And I picked out 3.03 and 3.385 because those are the two numbers that are listed that are on either side of the value that I got there. So I'm not. This is not any sort of a confidence interval or anything like that. But again, I'm just using that so I can sort of bound my p-value and figure out what that is. So the 3.385 and the 3.03, it's not a confidence interval or anything like that. I'm just kind of saying, using that to find what my p-value is. Any other questions you guys can think of on how we've done a hypothesis test here? Ah, good question. So another one came in. What would we do if alpha fell between? So what if I said my p-value was, what if I said it was between, oh, I don't know. So do you guys see what I think that so what do we do if alpha fell in between? So what if our alpha fell inside that range that we have 0.001 to 0.0025? Then you would want to more exactly calculate your p-value, which I'll show you how to do in a second here. But kind of going with our standard alpha levels of 0.05, 0.01, those. If you look at the table, those usual significance levels are sort of the endpoints of those intervals. So it usually won't fall in between there. You should be okay there. But that is a good question. And I will push that off for now. And I'll show you how to exactly calculate the p-value in just a second here. Really good questions. Yeah. Yes, so if the p-value is actually equal to 0.05, then you would go ahead and reject. So again, as long as it's less than or equal to. Is that what was said earlier? Yes, that is correct. And that's in your notes in chapter 15, I think. Okay, so one more example here before we round out chapter 18. This kind of goes back to an idea that we saw in chapter 9. So remember back in chapter 9 we talked about experiments. And one of the types of experiments we talked about was a matched pairs design, or matched pairs experiment. So in that, remember that we did one of two things. Either we found subjects who were very similar in maybe height, weight, gender, what have you, and then gave a treatment to each one of those. Gave a treatment to one or placebo to the other, or something like that. Or if we're in a situation, we could use the same subject for both treatments. So we do sort of a before and after type of a thing. So we give them one treatment, we wait a certain amount of time, and then we give them another treatment. So that's kind of our setup here. And the cool thing here is that we can actually use the procedures that we've just found to analyze this type of an experiment as well. So if we have a matched pairs, we can kind of do the exact same thing. So again, remember we're going to have, and we'll look at an example here, we're going to have observations on people that are either matched or the same person, either before and after. So we simply can find the difference between those two numbers and then do the same thing that we just did. So let's take a look at how we can go about doing that here. So our example here now, we're going to look at music and relaxation. I'm a big fan of music, so maybe I could get on board with this. Some researchers claim that music relaxes students and reduces stress while studying. Do you guys listen to music while you study? Sometimes. I feel like sometimes it's good, sometimes it distracts me. But anyway, so we take 12 students here and that we selected at random, and we find their initial resting pulse rate. And then each of these people participated in a month-long music listening relaxation therapy program. So after that program, then we take a final resting pulse, and we can look at these numbers here. So here are our 12 people. And for each one of them, we have their initial pulse rate, and then we do this month-long therapy thing for them, and we give them, we find another pulse rate. We find a resting pulse rate at the end of that thing. So the question that we want to know here says, is there any evidence that music reduced the mean pulse rate and consequently reduced stress? And then we're going to make some assumptions there about what the underlying distributions are, and we want a certain significance level. So again, to answer this question, what I said on the 2 slides previous was all I need to do is I can use the same thing that I just did. I need to find the difference between the responses within each pair, and then apply the one sample t procedures to those differences. So again, what I can do here is I can take the difference in their pulse rate. So I have their initial pulse rate and I have their final pulse rate. So what I'm going to do is I'm going to take their final minus their initial. So is that list of numbers? Okay, it is included in your notes. Good. And so now I can go about kind of doing the same thing that I've done before. So again, the question, I'm going to not go through this exactly here right now. The question's a little more stated for us already. So is there any evidence that music reduced the mean pulse rate and then therefore also the level of stress? So again, the question says that, or sort of the question says, does music reduce stress? So if I want to see if music reduces stress, and I'm looking at the final pulse rate and the initial pulse rate, how would I compare those two things to tell me that to say yes, music does reduce stress? How would these two things relate to each other? Would the final pulse rate be less than the initial pulse rate, bigger than the initial pulse rate? Less than, right. So I want to see if the final pulse rate is less than the initial pulse rate, which is the same thing as saying that the final minus the initial is less than 0. So if I want to see if their stress is reduced, I'll take their final minus their initial and see if that's in fact less than 0. And then maybe just note that I could have also taken, so up here in my difference, I've taken the final minus the initial, so I've already sort of set that up. But I also could have taken the initial minus the final and just see if that's bigger than 0. Kind of either way you want to do that is fine. Both will give you the same results. So just making that note. We're going to go with checking our final minus the initial, seeing if that's less than 0. Okay, so again here we can look at our data. We have these 12 numbers. There's a kind of a weird looking histogram of them. We have what the mean is, the standard deviation, and then some other things there as well. So again, kind of stating what the question is. I think we've already sort of done that. That's does music reduce stress? And by stress, I mean as measured in blood pressure or in pulse rate. So I just want to see if music helps me reduce my resting pulse rate. That one was kind of done a little bit for us already. So now I want to set up in my plan step, I want to set up my hypotheses and quickly check my conditions. So again, let's let mu equal the average difference between final and initial pulse rates. And actually, I'm going to write that again. I'm going to write mu with a final minus initial to remind us that we're taking the final resting pulse rate and subtracting off the initial and not the other way around. So just kind of remembering that's what we're talking about. So our hypotheses then are going to be the null and the alternative. The null is always mu equals something. The alternative is always involving that same mu. So maybe let's start with the alternative hypothesis. So what do I want to see about that mu, about that average difference between final and initial pulse rates? What do I want to compare that to? Right, I want to see if it's less than 0, right? So again, going back to this box right here. If I want to see if my final is less than my initial, that means that my final minus my initial is less than 0. So again, my alternative hypothesis is that it's going to be less than 0, and then I can fill in the same number in my null. So I'm going to assume that there is actually no difference, that the final and initial rates are the same, and kind of see what evidence I have against that. So in a matched pairs, they're never really going to, well, they will almost never tell you what the sort of hypothesized value is, but it's always going to involve 0. So I want to test the difference between these two groups, right? So I want to see, are they the same or are they somehow different? So 0 will usually be your mu 0 to plug into here. And I have not left myself any room. So again, I can check my conditions here. Do I have a random sample? Do I have a small enough? And is it large enough? So again, random is stated, good to go there. Small enough, 20 times n is 20 times 12, which equals 240. So is that less than all of the people in the world? Well, of course it is. This is less than all people. Actually, I guess we're talking about students here. So this is less than the total number of students that we have. And our large enough condition again here, n equals 12. So again, less than 40, which is means we don't have the easy way out here. But what's gonna save us here? Why can we still use our T procedures here? Yeah.
Is it because it's normal?
Yes, exactly right. So again, the example says we're making the assumption that the underlying distributions are normal. So sort of regardless of what the sample size is, we're in that smallest. Again, the three conditions we have over here. We're in that smallest boat now. So since the sample size is less than 15, we can use the T procedures as long as we have normal distributions going on. So since that's the case, we're good to go. Very well done. So but we have normal distributions. So we're good to go on all three of these things. Again, kind of want to get through this really quickly. So to actually solve this thing, remember our test statistic it's going to be a T, which is x bar minus mu 0 over s divided by the square root of n. And let's just make a note, x bar, mu 0, s, and n. X bar and s I can get from those summary statistics that were on that page with the histogram. It's at the top of page 8 there on your notes. My mean is negative 7.5, and my standard deviation is 7.66, we'll say. My sample size is 12, and I'm comparing this to a mu 0 of 0. Again, my null hypothesis says that mean is actually equal to 0. So I can plug these things in. I have negative 7.5 minus 0 divided by 7.66 over the square root of 12. If I punch that in my calculator, I will get that that's a negative 3.393. So again, my T is a negative 3.393. Sorry, I didn't mean to rush through that too quickly. And since we're running a little bit low on time, so our p-value. Let me go back here to the table. Sorry, I should have put this in there again. So ignoring this stuff at the top here, my t is now negative 3.393, and n is 12. Oh no, and I did not include that list, that row on the table. I have failed you guys. I'm sorry. Well, let's assume that we're looking at. Well, let's go down to 4. We always want to round down, right? So since 12 isn't there, 12 is actually there. I've just not included it. Let's go ahead and use that 4 row. You have it on yours. Okay, good. So I'll put it up here, but pretend that there's the 12 row is there. Thank you. So again, we want to look over here and find where the positive version of our test statistic lies. So we have a 3.393. So again, that's going to fall between, well, on my row it's here, but what are those two numbers that it falls between? So if we have the 12 row here, what two numbers does it fall between? Thank you. Sorry. The degrees of freedom, we actually want to use the 11 row. Thank you. That's a good catch. Sorry, I'm trying to go too fast here. So looking at the 11 row, what two numbers sandwich that 3.9393? So say that again, 3.106 and 3.497. Okay, very good. So then and which columns do those lie in?
99%.
And the 99.5? All right, so you should see in your 11 row, you should see a 3.106 and a 3.497 here. Is everyone there with me? So that just means my p-value is between 0.005 and 0.0025. So that means my p-value is 0.0025 and So that means my p-value is between 0.0025 and 0.005. So really quickly, again, my alpha, I'm going to use 0.05. And so since my p-value is, again, we don't know exactly what it is, but it's definitely less than 0.05. So therefore, I'm going to do what? Reject the null hypothesis. Very good. And then I conclude that, again, because the p-value is less than I'm going to reject the null hypothesis, and that says that there is evidence to conclude that music reduces stress, or the pulse reduces your pulse rate anyway. We're going to assume that makes you less stressed. So again, because our p-value is really small, less than 0.05, we reject the null hypothesis, which means that there's evidence to conclude that music does in fact reduce stress. So I'm out of time, but let me really quickly show you something over here. I'm going to switch over to the PC real quick. So if to show you how to actually calculate these p-values, you can Google t-distribution p-value calculator. And if you guys need to run, go for it. And this will bring up a list of things here. I think probably most of these will work. Maybe if we go here. Remember our t value in that last example was negative 3.393, and we had 11 degrees of freedom. And I can just click calculate. Boom, there's my p-value. My one-tailed p-value there is 0.003, which is indeed between that range that we found. So I'll send around this link. I meant to put it up here on the slides and ran out of time. But know how to do it by hand is important, but you can also do it like this, and it's just as good for your homework. On the exam, you need to know how to do it by hand. All right, you guys are out of here. Thank you so much. We'll see you on Friday.
So we should know how to